And I'll only briefly address FirstNet. I'm going to try to leave some time for questions at the end here. I'm going to zoom through some of the phenomenology just to level set some of our understanding of these things. Just a quick note on the panel. Unfortunately, Bron Cikotas could not be part of it. He was in the program. You can be praying for him. He went through heart surgery and he's recovering, but he's not entirely out of the woods. So for those who know Bron, please keep him in your thoughts and prayers. On the panel, we have actually far more distinguished folks than myself here as far as experience and knowledge. And so Dr. Baker has asked that I take the lion's share of the time because I'm the DHS guy. I invite you to look at his presentation from yesterday's tabletop and other online things. And then Mike Caruso has over 30 years, I believe, in this business and is one of the top EMP experts in the country for protecting against EMP effects. So I feel very privileged to be on a panel with these two gentlemen.
Feelings mutual.
Okay, well, thank you. Just a little bit on my background. I've been doing this a whole lot longer than I'd like to admit, in the decades time frame now, not as long as them, but I started as a blue suiter, back as an Air Force officer, used to be part of the Red Planning Board, and we would model EMP as part of that effort. And by the nature of that, I can't really go into details other than we considered it a very, very significant issue. In addition, I was privileged to be able to help start a program to EMP harden a lot of the senior leadership communications. So that was my introduction into EMP. Moving forward a few decades, as the FEMA Readiness Division Director, we started the IPAWS program. I think many of you are familiar with that. As part of that, when I went to Congress and tried to get justification, we pointed out that the EAS alerting network, which is, its purpose is to point out, when you're having incoming missiles from whatever source, you need to be able to operate through and alert the public. So we started an EMP hardening program at various sites with the helps of folks like Bron Cikotas, Dr. Radasky, and many others. I'll speak to that because that's a continuing program. In addition, currently I serve as the MAC team chief, which is modeling, analysis, and continuity at the NCCIC. We like acronyms, the National Cybersecurity and Communications Integration Center. So as that, or in that role, we model EMP. We are the federal lead for modeling EMP as far as communications impacts, and we have a series of mitigation programs. So let me dive in with a few of, next slide please, or should I am I driving this? Right hand button. Right hand, okay. So what we have here, as several have pointed out, is that there are three primary sources or vectors that create EMP. One is the nuclear weapon detonation, whether it be at high altitude, as very well addressed in the EMP Commission hearings and other documents. I commend those to you. The second, and one I want to mention on the detonation side, EMP Commission and most of the effort is focused on the high altitude side. The EMP from the source region or for a burst on the deck, that is very significant as well. It's not spatially as great, but if you're looking at the city or the region out to about 100 miles, even with the low kiloton weapon, you can have a lot of damage. Next is extreme solar storms. We've talked a lot about those. I'll just remind folks that weren't there yesterday that back just a couple years ago, we dodged a CME, a coronal mass ejection bullet, and it's more like we dodged a mountain of plasma that was dispersing through the universe, that had it gone off about 7 days earlier, we would have been in the direct line of fire, and we may not have been able to have the meeting today. The final form, and we were talking about it some very well here just a few minutes ago, is non-nuclear EMP or radio frequency weapons. There's a whole raft of those that are out there, some on the market. The Russians have been selling the Ronots E for quite some time now. Not the latest generation, but it's still quite damaging. You can get them in briefcases, and it goes into frequency realms and types that are much more complicated than some of the previous efforts we've done with just nuclear EMP, so I'm glad you pointed that out. As far as types of nuclear EMP, and I'm only going to focus due to time and other things, we're just going to focus on a few of the nuclear EMP effects. We've talked extensively already about high altitude, and I'll have some slides later on the source region. Next. Oh. Thank you for hers doing that. The E1 EMP, I've briefed a lot of folks on this over the years, and surprisingly, there's a large number of naysayers out there still that don't believe this effect is a real thing and that this is just a community that's trying to kind of like the self-licking ice cream cone. That is not the case at all. The Russians back in 1962 burst one during the Cuban Missile Crisis, amazingly enough. They burst one over one of their neighbors, Kazakhstan, and it had extensive damage to their infrastructure. I don't have time to go into it in too much detail. I have some slides that if you have some time later, you can look through some of the more detailed components of that. E2 is not as big of an issue other than E1 knocks out the protection perhaps that you typically have with lightning protection. And so E2 is something that we still need to consider. E3 is a very significant issue, especially for your larger yield weapons, and I'll have some more on that here in just a few minutes as well. The HEMP waveform is depicted here. At the high altitude EMP, you have three phases, the early time, which is up to a millisecond. You have the second or intermediate time that, the first time goes up to the millisecond, or microsecond, sorry, I'll get this right eventually. E1, microsecond, E2, 1 second, and then the E3 can go on for several minutes. I'll point out that people sometimes look at E3 and think, oh, it's not going to affect anything other than long lines over the continental landmass. Well, you have other systems like undersea cables that, surprisingly enough, especially in the shallower areas, you can get significant coupling into those important infrastructures as well. Here's a very common diagram showing that if you burst at different altitudes, you cover larger areas or smaller areas. At 400 kilometers, you've covered not only the continental United States, but most of the Canadian population and a good portion of the cities down into Mexico. This, what we call affectionately the smile diagram from Meditech, shows that when you have a burst, in this case about 400 kilometers above Omaha, that you get good coverage across the United States, again down into Canada or Mexico and up into Canada, and that the focus or the most intense area is in the smile area, strangely enough. The E3 coverage is also very extensive. I'll just touch on the bottom right-hand side of this due to time, in that if you recall the 1989 electromagnetic storm that was with the Hydro-Quebec incident, that was roughly 1 to 2 volts per kilometer. And what you can see is if you have a 1 megaton device at the proper altitude, you can cover an area that's close to the size of the contiguous United States. As far as what is the damage, what happens when you have an EMP, in this case, most of these effects that are demonstrated here are due to the E1 effect, but the trouble is mainly in the tails. And so, as like one of the Russian simulators has at their site, it's basically the tail's stupid. You've got power lines and you've got data cables like Cat5 cables connected into your equipment. And so where you're going to see these antennas, which are like Cat5 cables, a 100-foot Cat5 cable is a really good antenna. and it'll couple energy right into the NIC card or the network interface card, and in many cases, they would be blown. Some more examples from our testing. A couple quotes here. The DITRA, back last year I got this off their site where it says EMP would fry any electronics, laptops, sensors, and our planes, even a simple cell phone. Now, a qualifier is they're absolute experts in these areas. In fact, here's one of them. You know, I know you consult with them, but handheld devices are generally pretty resilient, whether it be a cell phone or other small device. And where it says it wouldn't kill a single person, it destroys the technology. Well, if you're up in a plane or without the technology, if the plane isn't functioning, it's a bad scenario, obviously. The testimony of the chairman of the EMP Commission, I'll just skip through some of these other than the bottom line here, where the EMP Commission found that within 1 year of a high-altitude EMP event, you could have upwards of 2/3 of the U.S. population at serious risk, and perhaps, and as he's saying here, they would probably perish from starvation, disease, and societal collapse. I'm not saying that that's the DHS position, but I am saying we are looking at that very, very seriously. Here is a redrawn graphic of General Loborev's presentation that he gave back in 1994. It was a great presentation in that it showed what happens when you burst one of these devices over a landmass. And just to summarize, when you have hundreds of kilometers of lines, whether they be power or communications, they found that, like on the communications line, every single relay on about a 500 click segment was blown. So you get things like that. The next one here shows that well, I guess this is dealing with the phone lines. Yeah, it shows that all repeater points were blown. And I think it's an important question at the bottom of the slide there, where we asked some of the Russians, have you fixed the problems with your communications infrastructure? And their answer was, all trunk lines, or those going between the major switches, are now underground, which was a Ministry of Communications initiative to protect the civilian communications. So when they tested it, they saw major results, and they started major programs to fix these problems. Oops. Okay. On the electricity side of the house, on the generation, they found that generators, and these are some of the backup diesels, that the E1 pulse was damaging those, as well as some of the substation electronics. In addition, and this is again kind of like the seawater, the E3 will penetrate the ground for a ways. And so where they had about I think it was 1,000 kilometer long power line that was buried about 1 meter under the surface, they had extensive damage on that line, and it actually set a power plant on fire. That is an important nuance in that a lot of times people think of EMP as destroying electronics. They don't understand that EMP also burns down power plants, or can. It can also set fires by the sparking and arcing, especially at the high frequency type. Next. From Russian history, and this is, won't read through all this, I'll just say, please take a look at what Kurt Weldon said back in 1999. I thought it was interesting that the former Soviet ambassador said during the Kosovo crisis that if you upset us enough, we are looking at EMP as one of the options. And I know one of the aides that was there said, and if one weapon doesn't do it, a few more will handle the problem. I know we have, I think, one individual who was actually at that meeting who's perhaps still here. So it's well known by Russian politicians as an option. Source region, I'll touch on this just very briefly. Sometimes you'll see where it says this is a 1 to 2 kilometer effect. That is very inaccurate. I mean, technically, if you're just saying the technical definition of a source region, yes, but it actually, the waves keep propagating. And when you do the coupling calculations into the infrastructures, which that's part of what my shop does, you find some interesting results. Like in this case, with a 100-foot Ethernet cable upset and damage, what we found is that there could be damage out to about 13 miles, and that you could have beyond 40 miles of upset to Ethernet systems. That's not saying that all systems within those rings would be down, but a significant portion could be down. And this one is just from a 10 KT weapon burst at ground level. So when you look at the physical destruction with a 10 KT, most of the damage is done in that first kilometer. The electronic damage is going out, as you can see here, beyond 10 and up to 40 some odd miles. Again, we bought some phones from Walmart, the little power adapters when we pulse those. You would think a cordless phone would be a great thing, and the phone survived fine, but those little wall plugs that do the AC-DC conversion, highly vulnerable to the effects. And so we were showing that even with the wrapping of the signal, the prediction was that you would have damage on those wall boards potentially out to beyond 70 miles. Again, that's not everyone, but that would be a significant issue. FM radio transmission, again, out to tens of miles of upset, actually in this case over 80 miles with the 10 KT, and then damage within about the 10-mile region. Next. Oops. Okay, hardening issues. We need to go beyond the current mill standards. I appreciate you bringing that out. There's a lot of emerging threats. We are working, like was brought out at the introduction, we've been working with the FirstNet community. Dr. Baker here has been helping quite a lot on helping to define other standards that we can use in that domain. If you don't use military standards, I do want to point out there are some very good international standards, at least for nuclear and some of the traditional forms of EMP. The IEC and Dr. Radasky have been doing some great work there. We need massively scalable, cost-effective approaches, and I'll get into something here in just a moment. Next. Some conclusions are that the risk of not protecting our critical infrastructures, in this case the communications one, is profound. One EMP burst over the continental U.S. Can disrupt from coast to coast. And a SREMP burst can disrupt communications within up to a 100-mile area, even with a low-yield weapon. It's relatively inexpensive if you do it up front, and even retrofitting is not prohibitive against the relative risk. We need EMP protection for more than just HEMP, these new emerging RF weapons, as well as source region EMP need to be addressed. We need massively scalable programs. We have internal to DHS and the federal community, and we've shared it with a lot of our industry partners as well. We have published an EMP protection guidelines for equipment, facilities, and data centers. It doesn't get into some of the esoteric, newer emerging threats, but it does handle the nuclear and the solar. Here's just a flavor. It's about a 45-page document right now. We have it broken down into 3 levels. And the thought here, and this is something I actually heard originally from Chuck years ago, that we need to not just try to use one size fits all, where you're using welders to try to handle everything. We don't have enough welders on the planet to handle the EMP problem. you have to come up with other creative solutions. So on the left-hand side is more the mill standard with some fire suppression and other things added in. Level 2 is where you are using Faraday cages against the traditional threats and fire suppressors for buildings. It's not much good if you have an EMP steel room in a building that burns down. You have to do it holistically. Level 3, which is much less, but because it doesn't have any Faraday cages, is you protect power and your antenna couplings and the like. Level 4 is basically almost the Walmart or Home Depot type of solution, where you go out and you buy 1 nanosecond rated surge arresters, put those in your facilities, connecting to all your equipment, as well as things like ferrites that you clip onto your Ethernet and power cables. So the mitigation efforts, we have put out guidelines. We're working with FEMA to help cities understand the source region EMP threat. The cities of Chicago, Houston, Baltimore, for example, we've conducted seminars with them. We are deploying and developing infrastructures that are EMP hardened. One is the EAS primary entry point radio stations that I mentioned earlier. Currently there's 34 of those stations are EMP protected, not in line like we're eventually wanting to go to, but a station engineer can come back after the event, and for long-term public alerting, we can address that need. And then we have other programs like the SHARES program, which I oversee, and we have Ross Merlin in the office, our audience here, who can address that. But we are trying to EMP harden HF, satellite, and other communications infrastructures through that. And we do have a full set of models for the traditional EMP threats, whether it be HEMP or SREMP. And I don't have time to go into those right now, maybe in the question period. Backup slides, I do want to just show that this is not a national planning scenario, but this is what we're using internally, like within the continuity communications community. This is like in one case, they said we need some scenarios to work around. This is an unclassified slide with a 1 megaton burst over the United States, and it shows damage rings where the orange is bad, yellow is pretty bad, and green is still actually not so good. But it says it's all bad. I hate to say it that way, but and the other thing is, wanted to show a couple other slides where you have a multiple EMP engagement, because you hear a lot in the literature about launches either from subs or ships off the coast or satellites coming from the southern polarly launched orbits or whatever. You may have a multi-dimensioned attack that isn't just a single burst going off over the country. And so we have some here, like this one is a 300 kilometer burst with a 25 KT, a 25 kiloton. And it's not an enhanced warhead, so most of it is green and yellow. In the next one, we have a 1 megaton at the same general location, and you see a lot more yellow and red. And it's covering most of the United States, and that occurs if you had a coastal launch. It would occur within about maybe a 4-minute period, depending on location of assets. If you do it at a lower altitude, like in this case, like the EMP Commission often would do things at like the 70 kilometer level. If you have it burst at 70 clicks with 100 KT, you'll see that most of the East Coast is impacted, and that would occur within about a 2-minute period. So you don't have a whole lot of time to react to these things. Okay, well, we've got a lot more, but I'm going to stop because I got to give the other guys some time. So thank you for your attention. Next up is Dr. George Baker, Professor Emeritus at James Madison University. And he's held rather senior positions in government. He used to oversee the EMP protection programs within the DoD. So with that, I'll quickly turn it over to George.
So I wanted Kevin. I'm really glad that he was able to take most of the time today. He was on the agenda last year and wasn't able to be here last year, so he's making up for lost time today. I just had a couple of charts. I just wanted to talk a little bit about the source region threat because it's one that's been neglected. It's one of the effects that's been misunderstood at very, very high levels. So. So there's a prevalent misconception. I see this over and over again when I read some of the scenarios that have come out of Department of Defense and Department of Energy, but that source region EMP effects are only important if the targeted systems are expected to survive. This is a direct quote. The primary damage-causing mechanisms of blast, shock, and thermal pulse. And these are what we normally call the hard kill effects, and they usually extend only 2 or 3, 4 kilometers away from the burst, depending upon the yield. And then another similar quote. These are direct quotes I've taken out of some fairly prominent government guidance. And source region is only concerned for military systems that are intended to survive. Both of these are wrong, so draw a red line through those. Those are not correct. Not sure I'm, okay, wait a minute. So, 3 o'clock? Yeah, that's what I'm doing. Okay, here we go. So when you have a burst on the ground, there is close end. You have a fireball, but you also have, just like with a high altitude burst, you have gamma rays that strip electrons off the very dense atmosphere. The gamma rays don't go very far at sea level, so the source region is only maybe 2 to 4 kilometers in diameter, or sorry, radius. The source region itself is very limited, very confined in its physical extent, but any long line that runs through the source region will experience, will couple extremely large peak currents running into the hundreds of kiloamps close in. And those currents will propagate to considerable distances. I'm showing, I went back through my archives, and this was an analysis we did for the Minuteman silos, but it shows the predicted current for an attack where you're seeing at 4 kilometers out, 25,000 amps, and even at 10 kilometers, you've got 12,000 amps. The other point to make about these source region currents are that the duration is milliseconds, not microseconds. So they will cook things. And then I had just brought along, this is my final chart, that here's a 10 kiloton low yield burst at 20 kilometers down a transmission line. What Kevin talked about, a transmission line running out from a scenario in Washington, D.C. And you can see that even at 20 kilometers, you're getting a 2,000 amps peak, a duration of several milliseconds. So, these are things that we need to factor into our planning scenarios for ground bursts as well. So that's all I had.
Okay, and Mike Caruso with the ETS-Lindgren. And I'll just turn it right over to you.
Okay, thank you. Thanks for having me here today. Just going to talk briefly about the facility part of protecting the communication system, because we've talked about protecting the grid, and that's certainly important. There's a number of things that have to be done all the way down the line to protect the communications capability and the facilities that actually house those communications. The prominent specification that is out there is the MIL standard 188-125. However, perhaps outdated it might be in some aspects. It's what we've got right now, and it deals with building a 6-sided shielded enclosure around the communications facilities. What we're seeing very, very quickly evolving is industry and commercial establishments looking at protecting their operations and their resiliency, their continuing operations. As part of the communications facilities, basically the communications facilities, the old central offices as they used to exist, are now data centers. And what we're looking at is basically protecting these data centers, and most of them are going to try to operate at a tier 4 level, meaning a 2N scenario where everything is backed up. You've got dual power lines coming in, dual lines going out for communications, dual capability on backup generators. One of the very important things that I did want to mention is that we've talked about harmonics. And harmonics are something that cannot be protected with the standard EMP protection. So GMD protection and EMP protection are just two separate issues that have to deal with. At this point, we advise our clients to use the very best UPS power conditioning systems that they can possibly have to try to deal with the second order harmonics that might be induced by the solar activity. The filters that are put in place with the protection devices will take care of the E1, E2 very nicely. When building a shielded facility like that, you really have to pay close attention to all the points of entry. The slightest hole in the shield can make the shield absolutely ineffective. And as was talked about, it is not possible to shield the transformer. Can't be done. So I'm absolutely in agreement with that. Anybody that tells you they can shield your transformer, well, yeah, move on. One of the challenges that we have in constructing these communications facilities is antenna interface. And many times the antenna or even a microwave link might be in band. So basically what our instructions are to our clients is that you really have to have a backup ready, something ready to put in place in case an event does occur. If something is in band, it's just, we don't know of any way of stopping it at this point. So having that at the ready. We as a company just recently completed an 84,000 square foot Tier 4 facility as a 6.5 megawatt facility, totally protected. It's been tested and certified by Little Mountain Test Facility out of Hill Air Force Base. The pulse current injection, all the components were certified prior to installation, and the installation itself has now been pulse current injected testing. So it is possible to protect within the limits and within the prescribed areas of Mil Standard 188-125. As was mentioned, IEC and Dr. Radasky are working on a more commercialized specification, something that is perhaps more user-friendly for commercial industrial world to help protect the facility aspect. So again, just close in saying, it's a multi-step process that we have to look at. We certainly have to look at protecting the power grid, protecting with any means possible the EHV transformers and the transformers down the line, but you also have to address the facility issues to make sure that the equipment within the facility stays running, and all of the support equipment. Can't lose sight of the fact that if you've got a data center, it does you absolutely no good to have power up if your air conditioning system has gone down. So thank you.